There is a place around every black hole where you can fall in but never climb out. Not because the walls are too steep, because there is no direction left that points away. Every path, every beam of light bends back inward. Cross it once and the universe behind you is gone forever. It has a name, the event horizon. The event horizon is not a surface you could touch. It is a boundary in space defined by a single fact, that the speed you would need to escape it is the speed of light. Just outside, a powerful enough rocket gets away. Just inside, not even light, the fastest thing there is, moves quickly enough. The door only opens one way. How big is that boundary? It depends only on mass. In 1916, while serving on the Russian front of the First World War, the German physicist Karl Schwarzschild solved Einstein's brand new equations and found the exact size. We call it the Schwarzschild radius. Squeeze any mass inside its own Schwarzschild radius, and it becomes a black hole. The numbers are hard to hold in your head, try anyway. To turn the sun into a black hole, you would crush it down to a ball 3 kilometers across, about 1.9 miles. The Earth, 9 millimeters, the size of a marble. Every object has a Schwarzschild radius. For most, it is unimaginably smaller than the thing itself. The idea is older than Einstein. In 1783, an English clergyman and natural philosopher named John Michell wrote to the Royal Society describing a star so massive that its escape velocity would exceed the speed of light. He called it a dark star. Light would fall back like a stone thrown upward. No one would ever see it shine. 13 years later, in 1796, the French mathematician Pierre-Simon Laplace reached the same conclusion independently. The largest bodies in the universe, he wrote, might be entirely invisible. For more than a century, the dark star stayed a curiosity, a clean piece of arithmetic with no known object to attach it to. The mathematics was waiting for the right physics. That physics arrived in 1939. Robert Oppenheimer and his student Hartland Snyder published a paper showing what happens when a giant star runs out of fuel. Gravity wins. The core collapses, and once it crosses its Schwarzschild radius, nothing in physics can stop it. It keeps falling, sealing a horizon behind it. The first true description of a black hole forming. For decades, these objects had no good name. Frozen stars, collapsed stars, Schwarzschild singularities. Then, at a lecture in 1967, the American physicist John Archibald Wheeler used a phrase that stuck: the black hole. Two words that captured both facts at once. It is black because no light escapes. It is a hole because things fall in and do not come back. Some hoped the collapse was a mathematical fluke, that a real, lumpy, spinning star would somehow avoid it. In 1965, the British mathematician Roger Penrose proved otherwise. Once enough mass falls within a critical region, a singularity and a horizon are not just possible. They are unavoidable. Black holes are a genuine prediction of general relativity. He won the Nobel Prize for it in 2020. Here is the strangest thing about the event horizon. If you fell through it, you would feel nothing. There is no wall, no membrane, no flash. For a large black hole, the horizon is a region of empty space like any other. You would cross the most important boundary in the universe without noticing the moment you did. Only later would you understand. But to someone watching from far away, your fall looks utterly different. As you approach the horizon, your clock appears to slow. Your image reddens, dims, and seems to hang there frozen, never quite arriving. This is gravitational time dilation, pushed to its limit. For decades, Soviet physicists called black holes frozen stars for exactly this reason. Both views are real. You sail through the horizon in a finite time, by your own watch. The distant astronomer never sees you cross at all. General relativity does not pick a favorite. Time near a black hole is not a single shared river. It bends, stretches, and runs at different rates depending on where you stand. The horizon is where those rates pull furthest apart. Falling in is survivable in principle, but the journey can kill you long before the horizon. Gravity pulls harder on your feet than your head. Near a small black hole, the difference is monstrous. It stretches you into a thin stream. Physicists call it spaghettification, and they are not joking. For a stellar black hole, you are torn apart well before you reach the edge. Strangely, the biggest black holes are the gentlest to cross. A supermassive black hole spreads its horizon across millions of kilometers, so the difference in pull across your body at the edge is mild. You could sail through the horizon of the giant at our galaxy's center completely intact, and only afterward face what waits inside. Bigger is, here, far safer. As you cross, the view changes in a way no human has seen. The entire outside universe, every star, every galaxy crowds into a shrinking bright circle above you, blue-shifted and brilliant. Behind and around, only darkness. The horizon does not appear beneath your feet. It closes over you, like the surface of water seen from below as you sink. Inside the horizon, the roles of space and time swap. Falling toward the center is no longer a choice you can refuse. It becomes as inevitable as tomorrow. At the very middle waits the singularity, a point where the equations of general relativity give infinite density and simply stop working. What actually happens there, no one knows. Our best theory hands the question to physics we do not yet have. The singularity is not really a place. It is a signpost that says, theory ends here. To describe a point of infinite density, you would need to join general relativity, which governs gravity, with quantum mechanics, which governs the very small. Those two great theories have never been reconciled. The center of a black hole is the clearest place in the universe where physics is still unfinished. You cannot photograph a black hole directly, there is nothing to see, but you can photograph its silhouette against the glowing gas around it. On the 10th of April 2019, the Event Horizon Telescope, a network of radio dishes spanning the whole Earth, did exactly that. The galaxy Messier 87, 55 million light-years away. A ring of fire around a circle of dark. That dark circle is not the event horizon itself. It is the shadow, and it is larger, about 2.5 times wider than the true horizon. Gravity bends the paths of light so severely that the black hole hides a region bigger than itself. The bright ring is light that has looped around the back, bent toward us by gravity before escaping. 3 years later came the harder target. On the 12th of May 2022, the same telescope photographed Sagittarius A-star, the black hole at the center of our own Milky Way. 4 million times the mass of the Sun, 27,000 light-years from where you are sitting. A second ring of fire, this one at the heart of our home galaxy. Long before we could photograph one, we found one by its violence. In 1964, a rocket flight detected powerful X-rays from the constellation Cygnus. The source, Cygnus X1, turned out to be a black hole of about 21 solar masses, tearing gas from a companion star. It was the object Stephen Hawking once bet against, and in 1990, he conceded he had lost. For most of the 20th century, everyone agreed a black hole was perfectly black. Then in 1974, a young Stephen Hawking did the calculation that made him famous. Bring quantum mechanics to the edge of the horizon and it is not black at all. It glows faintly with a temperature. Black holes radiate, and if they radiate, they must slowly evaporate. The glow is impossibly faint. A black hole the mass of the Sun would have a temperature of about 60 billionths of 1 Kelvin, far colder than the empty space around it. The bigger the black hole, the colder it is, which means the giants do not evaporate. They grow, feeding on the warm universe, and will only begin to shrink in a future almost too distant to name. But evaporate they eventually will. A black hole the mass of the Sun would take about 10 to the 67 years to vanish entirely, a one followed by 67 zeros. That is so far beyond the current age of the universe that the comparison is meaningless. Yet the physics is clear. Given enough time, even black holes are temporary. Nothing is permanent, not even the dark. Hawking's glow confirmed a daring idea from 2 years earlier. In 1972, The young physicist Jacob Bekenstein argued that a black hole must have entropy, a measure of disorder, and that it is written on the area of its horizon. The bigger the horizon, the more it can hide. Black holes, it turned out, obey the laws of heat, just like a steam engine or a cup of tea. And that raised a terrible problem. Quantum mechanics insists information can never be truly destroyed. But Hawking's radiation seemed to come out blank, random, carrying no memory of whatever fell in. Burn a book inside a black hole, wait for it to evaporate, and the words appear gone for good. In 1976, Hawking argued that black holes erase information. Most physicists were horrified. The fight lasted decades. One escape route came from the holographic principle, proposed by Gerard 't Hooft and Leonard Susskind. The idea that everything inside a volume of space can be encoded on its boundary, like a hologram on a flat sheet. Perhaps the information never falls in at all. Perhaps it is smeared across the horizon, waiting to leak back out. In 2012, 4 physicists sharpened the paradox into something brutal. To keep information safe, they argued, the gentle horizon might have to become a wall of fire, a sheet of lethal radiation that would incinerate anything crossing. This firewall would break Einstein's promise that the horizon feels like nothing. The choice seemed to be lose information or burn. Neither was acceptable. Slowly, the tide turned. New calculations suggested the radiation is not blank after all, that subtle correlations carry the information out, if you know how to read them. In 2004, at a conference in Dublin, Hawking publicly conceded a long-standing bet and admitted that black holes probably do preserve information. He handed the winner an encyclopedia from which, he joked, information can be retrieved at will. The deepest progress came only recently. Around 2019, several groups found that when you account properly for quantum gravity, the information content of the radiation follows a curve, rising, then falling back to zero exactly as quantum mechanics demands. Regions called islands, hidden inside the black hole, turn out to belong to the radiation outside. The paradox is not fully closed, but the arithmetic finally adds up. Why does any of this matter? Because the event horizon is the one place in the universe where our 2 deepest theories are forced to meet and to disagree. General relativity built it. Quantum mechanics makes it glow. Resolving how they fit together at the horizon is, many physicists believe, the road to a theory of everything. The black hole is a laboratory we cannot enter, asking the hardest question we have. Black holes are not rare. Our galaxy alone holds an estimated 100 million of them, the collapsed cores of long-dead giant stars, drifting silent and unseen. The nearest known one, called Gaia BH1, lies about 1,560 light-years away, close, in galactic terms, though far beyond any reach of ours. The sky is quietly full of horizons. We even hear them collide. In September 2015, the detectors of the Laser Observatory called LIGO felt the space-time tremor of 2 black holes spiraling together and merging more than 1 billion light-years away. The first gravitational wave ever recorded. 2 horizons became one, in a fraction of a second, releasing more power than every star in the visible universe combined. Everything we have said is now testable and tested. We have weighed black holes by the orbits of stars around them, work that won the Nobel Prize in 2020. We have heard their collisions. We have photographed the dark circle of 2 of them. The event horizon has graduated from a frightening idea in an equation to a measured feature of the real sky. So picture the fall one last time. No wall, no alarm. The stars above gathering into a brilliant point, the dark closing around you like rising water. By your own watch, the crossing takes a moment. To everyone left behind, you simply fade, redden, and hang at the edge forever. A frozen image on the last surface light can leave. That frozen image is real in a sense. The last photons you ever emit, just before crossing, climb out exhausted and stretched, arriving at distant telescopes redder and fainter for as long as the black hole exists. A black hole remembers the light of everything it has ever swallowed, written, dimming, on the surface of no return. We have mapped the boundary in exquisite detail. We have photographed its shadow, weighed its mass, heard it ring. And yet the one place it all points toward, the singularity at the center, the moment our equations fail, remains hidden behind the very horizon we have learned to see. The black hole shows us its edge and keeps its heart. So they hang there, all across the sky, 100 million silent horizons in our galaxy alone, each one a door that opens only inward, each one a question physics cannot yet answer. We have learned to photograph the edge of the abyss. We have not learned what lies at the bottom. The universe is not obliged to make sense to us. The event horizon is out there, dark and patient.